computing. And so it's a pleasure to be speaking to you today. I have some prepared slides here, which I can put up. If I could get permission to do sharing, that would be great.
Give me a second.
Sure. It might be helpful to hold questions until the end, because I might answer your questions. And also, if you could also just keep yourselves on mute, that might cut down on the background noise. Good. So let me share my slide there. Good. And there. Can you all see that then? I think fantastic. So so thank you again for having me. And I'd like to tell you a bit about tKet, which is the quantum development kit that we've developed at Cambridge Quantum Computing. And I'd first like to share just a few basic facts about us. We were established in 2014, which makes us one of the oldest quantum computing companies. We focus on quantum software. Because of that, we have partnerships with all the major quantum hardware providers like IBM and Honeywell and Google and Microsoft and such. We're especially close with IBM and Honeywell. In fact, we can resell time on their machines. Our software focuses on the compiler, which I'll be telling you about today, as well as chemistry and machine learning and cybersecurity. We were primarily based in the UK, but we have people all around the world. We have a few people in Tokyo. I'm based here in Portland, Oregon. And the big news announced about a month ago is that we are merging with Honeywell's quantum group. So Honeywell has a fantastic quantum hardware group, and we have a great software group. And so in the next few months, we will be forming a new company, which doesn't have a name yet, to form the world's first complete quantum solutions provider. It will probably have about 350 people, which will be by far the biggest quantum group in the world. So we're very excited about that, and keep watching the news for any updates. So I think many of you are probably familiar with the basics of quantum computing, at least, but let me just quickly summarize it again. Normal computers work with bits, which are like the sides of a coin, heads or tails. Quantum computers work, you can again think of it as a coin, but instead of heads or tails exclusively, it's sort of like a flipping coin in space, where it can be in between the 0 and 1, or the heads and tails. And when you combine this idea, which is called superposition, with another concept from physics called entanglement, you can get a huge number of states that you can consider at the same time. And there are some problems that can take advantage of this. And so that's why quantum computing is so exciting, because we can solve these problems we never could have hoped to have solved before. A prime example is in chemistry. And this was actually the very first problem that was identified for quantum computing. So suppose you have my favorite molecule, caffeine. This isn't a very large molecule. It has only 24 atoms. But if you were to simulate this on a computer, you would need a huge computer, about 1 to 10% of the size of the Earth. And it's not because it's like the equations are so complicated. They're not. In fact, we've known what the equations are for about 100 years. It's that as the molecule gets bigger, you have more and more atoms, and every atom has several electrons, and they're all interacting with each other. And so when you write down the equations for all of those interactions, that becomes very complicated to solve simultaneously. And so that's why you need such a big computer. So it would be theoretically possible to do it. It would just be impractical. But when you look at something like penicillin, which is about twice the size, you would need a computer about the size of the whole universe. So even theoretically, you couldn't do this type of thing. And so this is why quantum computing comes into play, because it's not just a faster computer. It could solve problems that we never could have hoped to have solved using normal computers. And so that's really why it's so exciting. These quantum computers really do exist. They're not just science fiction, fantasy ideas. They really do exist, and we know of over 100 quantum computers in the Western Hemisphere alone. There's lots of different approaches. So one idea is superconducting, another is ion trap, and there's photonic, and then there's a few assorted ones. And there's many companies and groups using these. And each of these approaches has their own advantages and disadvantages. It's not just the number of qubits that's important. It's also important to include the quality of the qubits. And there's been this one metric called the quantum volume, which has recently been defined by IBM, which takes into account lots of these features. So it's not just the number of qubits, it's also the quality. So this is kind of an overall single metric for the power of the quantum computer. And the progress in this is really extraordinary. So this is a chart of the quantum volume over time. And I think many of you are familiar with Moore's law, which has shown that quantum computing, normal computing has doubled in power every 18 months or so. And that's held true for decades. Quantum computing is on a much faster trajectory. So quantum computing has doubled in power at least every 12 months. So that blue line there shows what IBM has done. And the orange line is the progress made by Honeywell. And they think that they can increase the quality by a factor of 10 every year for the next several years. And then that yellow dot up there is IonQ. They claimed a few months ago that they've developed a processor with a quantum volume of 4 million, which is fantastic if it's true. I just put an asterisk there because it hasn't been confirmed by outside groups, but they're a fantastic team, and so I have no reason to doubt it. So, so regardless of the details, the next few years in quantum computing should be very exciting, and there's a lot of progress being made. Right now, we don't have the quantum computers of our dreams. We do have quantum computers, and they do things which would be difficult for a normal computer to do, but we have to be aware of the constraints. And so these constraints are such that we have maybe 50 to 100-ish qubits. The error rate is still relatively high. We can't do something called error correction, which means that's when you spread the information out among several qubits in case one qubit does something wrong. So we can't yet do that. The qubits often have some sort of constraint that a qubit is only able to interact with a few other qubits nearby. And so for these reasons, a lot of emphasis has been going into hybrid algorithms, which means that you use a classical computer as well as a quantum computer together to do this. A lot of the heavy lifting is done by the classical computer because they're more powerful right now, and only a few special commands are sent to the quantum computer. And so so I'm emphasizing this for a reason. So the idea of all this is called NISQ, or noisy intermediate scale quantum. And so that's where we are today. And so, so moving on to compilers, I think many of you have enough familiarity with computers that you understand what a compiler is. You, as a human programmer, you write a program, you can understand it, right? Humans can understand it. A computer can only understand binary. At the most basic level, everything that a normal classical computer understands is just binary. And so, so there needs to be some sort of translation made between what you write and what the computer understands. And this is true for classical computers, and it's also true for quantum computers. And a good compiler doesn't just make that translation, it does it efficiently, right? Because you want to use it as little memory as possible, and you want the program to run as quickly as possible. And so this is why we developed tKet. And so this is a quantum compiler, and it sits in between the algorithms that you write, the programming that you write, and the actual quantum hardware or simulator. So just like where you would expect. And here I've put a few logos here of popular quantum hardware and simulators that you might be using. So what does tKet really do? So tKet allows you to use your favorite quantum programming language like Qiskit or Cirq or Q# or what have you, and it allows you to execute it on whatever quantum hardware you'd like, IBM, Google, Microsoft, what have you. And all of the details of those quantum hardware platforms, tKet knows, and it does automatically. And for reasons I'll get into in a moment, there are a lot of differences, and it can be very confusing. If you wanted to write a program on, say, IBM's platform, you would have to use the Qiskit developed by IBM. And then if you wanted to move that to Google's computer, you would have to use Cirq. And Cirq is similar to Qiskit, but there's little differences. And so you'd have to rewrite your program, and you'd have to be aware of all the nuances on the Google device and how it differs from the IBM one. And all these things that you don't really want to fuss about, tKet will take care of for you. It's completely invisible to you as the programmer. And so that's why it's so powerful. There are other compilers available, but this is a comparison showing the platforms that tKet supports compared to the others. And you see that tKet is by far the most universal. So with the other languages, you're pretty much locked in to using one or at least a few of different platforms, depending on the language you use. tKet allows you to use almost all of them. The only notable exceptions are D-Wave, because that's an annealing platform, which is very different from the gate-based approach that we assume. And Quantum Circuits Inc., we're in discussions right now with supporting it. We just don't have close enough relationship with them yet. But all the other platforms we have partnerships with, and we automatically update tKet to reflect the latest changes in their platform. So what does tKet actually do? How does it do this compilation, and why is it superior to the other quantum compilers? So tKet executes your program as efficiently as possible, and it does this in two different ways. So the first way is circuit optimization, and the second way is by solving constraints. So let me talk a little bit more about that. So with optimization, this is on your quantum circuit. So this has nothing to do with the hardware that you're going to run it on. It looks at your quantum circuit and it looks for ways to simplify it. So it looks for patterns in your circuit, and it looks for ways that it could remove the gate. So a very obvious example would be if you had two Hadamard operators in a row. This is mathematically identical to nothing, to just having a unity operator, right? And so so it can remove those two Hadamard gates. So that's a very simple, obvious example. There's others which are less obvious, which I'll show you in a moment. And tKet has all these programmed into it, so you don't need to worry about that. So it does what's called the people optimization. It goes through your circuit and it looks for little patterns of ways to simplify the gates. And then the second thing it does is it's more macroscopic. It's aware of more sophisticated ways to simplify your circuit. It looks for patterns, and so so it has some tools built in for that. So this is an example of the people optimization. So you see on the upper left-hand corner, this is two C0 operators in a row. And just like with the Hadamards, these two undo each other. They're inverses of each other. And so those can be removed, and so you have nothing at all. So you've gone from two gates to nothing. And of course, that's good because the circuit will run faster and there's less chance for an error. The other examples shown here are not quite as obvious, but if you're patient, you can work through the mathematics of this. You can see that these are mathematically identical. And I've given a paper here, which is a technical article, which describes some of these other patterns. If you're curious, you can take a screenshot and look up the paper later. So so again, all this is done automatically. The second thing that it does is, once it has the most efficient circuit, it looks for the most efficient way to implement it on the hardware that you've chosen. And so to do that, it has all the information about the way that the qubits are connected on your quantum hardware, and it maps your circuit into that physical architecture. And again, it knows all the details for you. You don't have to even think about that. Now, to understand why this is so important, these are a few different quantum architectures of popular platforms. These are all superconducting, so they have something in common. But you see the way that the qubits are laid out is very different. The Google versus the IBM versus the Rigetti machines, you see that the qubits are connected in very different ways. And that may influence how you run your circuit, of course. And it's not just the way that the qubits are connected, the gates that they use are very different. And these aren't necessarily the gates that you would be using in your circuit, right? And so so tKet will automatically translate the gates that you've been using in your circuit into the native gates for that architecture. So so this is just a simple example. Again, tKet has all this built into it. Now here's an example of a problem that might come up. So on the top part of the screen, this is IBM's Melbourne device, and you see that each qubit here is talking to at most 3 others. So this has at most a 4-qubit coupling. The circuit shown on the bottom half of the screen, this has some 5-qubit interactions. So you see that those 2 qubits on the bottom, they each need to talk to 4 other qubits. And so naively, you might think, well, there's no way I can run the circuit here on that architecture, right? Because I need 5 qubits coupled, and this architecture only supports 4. That's not actually true. It is possible to do this, but you need to be a little bit clever about it. The way that you do this is that you have these swap operations. You can actually move qubits around. The cost of this is that you have to use C0 gates, which of course take a little bit of time, and there's a chance something can go wrong. And so it's computationally expensive, and you need to do this optimally. And so so tKet has a built-in optimizer to find a way to efficiently do this. And so it moves them around and it finds the most optimal way to map your circuit onto the architecture that you've chosen. It's not just CQC that uses this for our internal quantum algorithm development. We do, but many groups around the world have been using this. So so IBM and Google and CERN, in fact, have been using this. And these are a few of the academic articles that have been written about the performance of tKet. And you see that it's quite a bit favorable to some others. This was a benchmark recently done by Arlene. They compared tKet to other compilers like tKet and circ. So on the left-hand side, this shows the gate count reduction, and you'll see that there's quite a few less gates needed if you implement it on tKet compared to the others. And on the right, this is a comparison of the execution time. And I want to point out that the vertical axis here is logarithmic. And so tKet, there in the middle, it's not just a little bit faster in the execution time, it's orders of magnitude faster. And the reason I emphasized NISQ earlier in the presentation was because we have so few qubits right now, and the error rate is sufficiently high, that having an efficient runtime could mean the difference between running your program and not running it. Because if you have too many operations and it takes too long to execute, something is probably going to go wrong, and there's no point in even running it. And so that's why, especially in this NISQ era, it's really a good advantage to be using tKet to have your program run efficiently. We are constantly updating it. We are on a monthly cadence, roughly. So every month we update it with the latest features. Some of these are because our hardware partners have updated their hardware, and sometimes it's because we've added new features to increase the efficiency. The big announcement about 3 months ago was that we removed all licensing restrictions. So tKet is now available for free for anyone to use. You don't need to get a permission or anything. You can just download it, and I'll show how you do that in a second. The only thing that we ask is that you give us feedback on how we can make it better. And if you write an article using tKet, you just credit us in the acknowledgements. That's it. But no money or licensing or anything like that needs to be taken care of. In the future, we're going to be unveiling several new features. So the first is called Kermit, and it's an error mitigation toolkit. So we can't quite do error correction yet, but we can do error mitigation. We can reduce the errors that you're likely to have. We are moving to the cloud. So right now you need to download it and it will run locally on your computer, but we're working on having a sort of software as a service where you go to the cloud, you'll automatically have the latest version. It would be very easy to interface with things like Amazon or Microsoft's Azure, like other cloud platforms. And it would be very easy to collaborate. We're also starting to think about error correction. And in fact, we're already starting to build a team to build this in. So this is how you can download it if you'd like to take a screenshot there. So again, it's free and available for everyone. Just go to GitHub and download it from this repo here. The repo includes lots of documentation and examples. So it's everything that you would need to get started. And you just use the normal pip install. You do pip install pytket, so that's the Python version of this. You also just need to install the module of whatever hardware you think you might want to use, like IBM or Honeywell or whatever. So we have all of those available. You just download the ones you want. So that's and let me just mention one more thing. It can be expensive running your program on real quantum hardware. So for example, if you went to IBM, you would need a 3-year contract and it would cost millions. Because of our close relationship with them, we can offer access to this in more affordable terms. So this would be for IBM, for example, 6 months, and you would share the premium hardware devices with 3 others. One of them would be us. So we would work on a project together, and it's much more affordable. It doesn't cost millions. And so especially for academics or for startups, this might be much more feasible. And if you'd like to talk to Honeywell, of course, we can introduce you. And in a few months, we will be all one team with Honeywell. So that is it for my prepared remarks, but I'm happy to stick around and answer any questions that you might have. Does anyone have any questions?
I have a question on like some technical details of the optimization.
Sure.
So I've been looking around to different software and different like decomposition schemes of like the Entafali, which is like Tafali gates with multiple control bits.
Yep.
Do you have did you know what the complexity of decomposition in terms of CX that tKet would decompose these gates to?
I don't. If you can send me an email, I can pass that along to our technical team who can answer that.
Okay, thank you.
There's a question on the chat. Could you speak about CQC's work in QNLP? Yes. So natural language processing, I think many of you know, is the process where you convert how we as humans speak into something that the computer can understand. And this is how Alexa and Siri and chatbots and such work. So CQC, to my knowledge, we're the only commercial group working on this. A few months ago, we hired Bob Cook, a professor at Oxford, and his team. And so they're now looking to commercially apply this so to quantum natural language processing. And it's a very natural adaptation. So it turns out that the mathematical structure behind natural language processing very well adapts to quantum computing. And so, so yes, we're very active in the quantum natural language processing area.
I have a question about the technical, so for example, you said that tKet allows you to, for example, I use Qiskit exclusively for my code, right? But if I want to use Google Computer, for example, right, I can do that through tKet. Is that what you're saying?
That's exactly right. In fact, you don't need to stop using Qiskit. You can go ahead and use Qiskit, just also install tKet. Right. And so yes, tKet will allow you to program in Qiskit, but run it on Google's machine, provided you have access. So yeah, this assumes you already have access to those machines. This just executes it, yeah.
Right. So that means that I don't have to learn circ or different other.
Correct.
Okay.
Correct. Yeah. In fact, that's what most people do, is that they use Qiskit and tKet, and then they run it on whatever they want.
Nice. Yep. That's great. Does tKet support Qiskit Pulse or no?
I don't think so. I will check on the latest of that, but I don't think it supports the more lower level things like the pulse control.
Right. So it's high level, gate circuit.
Correct. Yeah. It's more high level. Yeah. I don't think we yet support the pulse stuff. There's a question, can it also generate, for example, Q# code from Qiskit? Yes and no. If what you're asking, can I run it on Microsoft Simulator from Qiskit? The answer is yes. It doesn't actually translate it from, say, Qiskit to Q#. It just translates whatever you're using, Qiskit or Q# or whatever, it compiles it to an intermediate representation and then executes that. Let me just put my email address here in case you have any further questions. So just from any code to any backend, yes, that's true.
So I just an announcement for you guys. So I made you guys be able to unmute yourself. So if you have any questions, just go ahead and unmute yourself and ask. It's Jackson.
Hi, Jackson. Hi, Mark. Sorry. I had a question about the optimization. So tKet has two steps of optimization. One is to optimize the circuit itself, and the second is to optimize the circuit for the hardware it's running on. So my question is it possible that the first optimization step could interfere with the second optimization step, that somehow you optimize to a circuit which is not very efficient on the basis gates of the hardware?
That's an interesting question. I can't imagine a case where it would get worse, because the first part reduces the gate count, and then the second part runs it on that one. So I can't imagine a case where reducing the gate count would make it worse on the hardware. That's an interesting question, but I can't think of a real world example where that would really happen. I'll check with our science team.
When you talk about gate counts, are you referring to double qubit gates and that kind of stuff, or just general gate counts?
So 2 qubit gates or even single qubit gates. So they have typically different error rates and different time to execute and everything. But yeah, we're trying to minimize everything.
So so the metric is just the combinations of those two things.
Yeah, I think it's just the sum of them. I don't think they weight them differently. Yeah.
Right.
Yeah. How is PyTicket? Is it different in Transpile in Qiskit? So you're asking how PyTicket is, how it transpiles differently from Qiskit, I think. So they, yeah. So yes, they do basically the same thing, but tKet has far more features to make the compilation efficient, and tKet allows all this switching platforms easily. Whereas Qiskit, you're pretty much locked into using IBMs or one or two others, but tKet is much more universal.
So I was wondering, so if I have a circuit, right, and it's like a really long circuit, and for example, it's like multiple control bits, right, and I send that to IBM's machine, right? So would it go through IBM Transpiler, then it goes to tKet, or how would it work? Would it just go straight to IBM or like the machine that's running it on?
Yeah, it sends it directly to the machine that it's running it on.
Right. But does the transpiling of IBM interferes with that of tKet, or is that like two separate things?
No, I think those are two separate things. Yeah, I don't think they interfere with each other.
Right.
Is tKet open source?
That's a good question. So right now it is open license, so anyone can use it for however they wish. We're looking into the open source process. So right now, no, but in the future it might be more open source. Yes.
It's quite nice. I was just wandering around. I saw this random module in Qiskit, and it had something to do with CQC.
Yes. Is this for generating random numbers?
How would it be different from something like Qrand, which is open source and random?
Sure. So when people talk about random numbers, usually what they're referring to is a pseudo-random number, because classical computers can't do anything random. They just follow a formula. And so what is usually done is there's some formula which based on like internal settings, like the number of milliseconds since you turned your computer on or something, it produces numbers which look random casually. And most of the time that might be okay. But if you were doing something like cybersecurity and you needed to generate a random key, you need to make sure that that number is not just random, but no one else could possibly know what that number is. And so for that, you actually need quantum physics. So there is a way to do this in quantum physics. And there's even a way, if you use entanglement, you can prove mathematically that no one could possibly know what it is. So there's actually a mathematical check you can do. And so the past few years, we've been developing a technique which we call Iron Bridge, which uses entangled qubits to generate random numbers in a way that you can prove that no one could possibly know what those numbers are. And so that random module is something that we developed. I believe it's still in its beta testing mode through IBM. So you can use it, but we don't recommend using it commercially for your cryptographic keys or something.
So I have a question. You mentioned that tKet takes into account the coupling of the device, but does it also take into account like the error gates, like the single qubit and the CNOT error?
Yes, it does. Yes, all that information it takes into account when it figures out the mapping.
Okay, nice.
That's a good question. There's a question in the chat about what are the opportunities in CQC for internships for undergrads? So we do have internships. Every summer we do this. We make decisions around December for the next summer. So I'd recommend sending in your applications this fall with your interest in that. In the past, the interns were physically located in the UK, so you needed a UK work permit. This summer, of course, because of COVID, things got kind of changed around a bit. And then now that we're merging with Honeywell, and they're based in the US, I don't quite know what the situation is, but if you're at all interested, I would encourage you to apply.
So what kind of work would like an internship be at like CQC? Is it more like hardware side? Well, obviously it's like not right now because you guys are like focused on software, right?
Yeah,
but it's more
yeah. All the interns we had were focused on software because that's all we did before. I don't know how it's going to work with Honeywell. They develop hardware, Yeah, and then the next question, what's the procedure for that? So anyone who's interested is welcome to apply. It's pretty competitive. We only take a few people, and we give them real projects to work on. And of course, we're looking to identify talent that we can hire, because we are expanding quite a bit. We have about 150 people now, and especially in the US, we're looking to hire. So it's a great opportunity, but it is pretty competitive. But again, if you're interested, I encourage you to apply.
I had another question about the optimization.
Sure.
So near the end of your presentation, you mentioned how you're not currently dealing with error correcting as of yet.
Mm-hmm.
So I'm wondering that in the process of trying to get error correcting, how will that affect your optimizations? Because as far as I know, there's no universal gate set, which is also transversal with error correction. So how would you take that into account?
I don't think we would do anything different. So with error correction, you still have the logical qubits, of course, and then you're just replacing that with the physical ones with this complicated process. So I think you're still trying to make your circuit as small as possible and execute it as efficiently as possible. I don't see any reason why the error correction. Well, okay, that's not quite true. With the error correction, of course, you're having several qubits represent one, and so the way that it's physically mapped, that would affect how you do that. So yes, I guess there are subtleties there, but again, we're just now starting to look in that direction. We haven't been able to do it before because there was no point.
Okay.
So like, I think I saw on your first slide when you talk about NISQ that it's the error of like 50 to 100 qubits, but like, are we already there yet, or are we like not? Or is it something that we're getting into as of now?
For error correction?
No, for NISQ. For like you said, there's like 50
so
to 100.
we're in the NISQ era right now. So computers nowadays have about 50 to 100 qubits, but the error rate is still too high to use error correction. If we tried to do error correction now, it would actually get worse. And so there's no point in doing it. And so in a few years, we think we could be at the area where we could do error correction. So we are starting to look in that direction, and we're starting to hire people to build that into tKet, but we don't actually do it in practice yet. Is there any chance that more complex gates can be built in real life rather than breaking it into simpler gates? Well, so recall that the way that it works is all operations on the quantum computer are really just manipulating qubits. And so depending on the way that that's done, the way that you've built these qubits, there's a few simple procedures you can do, and then other gates are built out of that. And so you can define complex gates, but at some level, you need to tell the machine how to manipulate things, and that's going to be a series of simple commands. And so that's why it will still probably be broken down into the gates that we recognize.
Is the hardware level decomposition an exact decomposition of the gates, or is it a very good fit?
That's a good question. It depends. There are approximations that can be made. So like when you're trying to rotate it by some angle or something, depending on the error that you're comfortable with, you can like if you're fine with a 2% loss in the accuracy, then you might be able to reduce the gate count quite a bit. So there are approximations that you can use depending on your comfort level.
Do we have control of that? For example, say if I want like if I want like a 2% error, so I'm comfortable with that. Can I tell tKet to build that in? Oh.
Yes. So for example, I know that the KEK decomposition, which I think says that any 2-qubit gate can be reduced into 3 C0s at most. I think there's an approximation you can do, and you can specify how comfortable you are. Yeah. Are there any?
Would decomposition, like decomposition of like complex gates into simpler, would that lead to like higher error loss or like change in the values?
Yeah, the more gates you use, the more likely it is that something will go wrong. And so you always want to have as few gates as possible. Yeah.
Okay. Is that the reason why like more complex systems aren't built?
Yes. Yeah. So so for example, if the error rate, so if the quantum computer right now has like a 99.5% fidelity, so that means about 1 in every 200 operations, something is going to go wrong. So you can't have more than about 200 operations, like gates in your system, because something is probably going to go wrong. And so that's oversimplifying it, of course, but that shows how this limits us to very simple circuits right now.
So right now, is there any sort of functionality inside of tKet which would alert the user if the circuit that they've written would exceed the lifetime or the coherence times of the target system?
I don't think so. I don't no, because you could be running it on a simulator, and then you can tell the simulator act perfect or be a little more realistic in how you simulate things. So tKet itself doesn't care; it will just compile the circuit. But if you try to run it on real hardware, you'll just get gibberish because things will go wrong and decoherent stuff.
Okay.
Yeah. So thank you again for all your questions. I've written my email address there in the chat if you'd like to follow up with anything else, especially more technical questions that I can't answer. I'm happy to pass them along to our scientific team. So thank you again, Adam, for organizing this. And it was great to talk to you all.
Well, thank you very much. Have a nice day.
All right.
For the talk. It was great. Thank you.
I think you can stop recording now.
Yeah.